Good morning, everyone. Welcome to this DigiPro Breakfast Webinar with the title Falling Management for Combustion-Thermal Power Plant. We have arranged this so we will have an introduction by Mika, and then Istvan will go more deeply into the modeling, and Anders, he will then talk about the sensing that has been used in this project. I also would like to mention that this is a DigiPro webinar, but it's supported then by COGNITWIN, which is one of the associated projects in DigiPro. So this is how we work. We pick out associated projects that is relevant for the process industry and select issues and themes from the project. So we all get known of the results, and maybe also we can have some implementation of what has been developed in this associated project. This webinar has also been supported by the Research Council of Norway. Just having said that, so thank you to all of these partners. And then I think I will give the word to you, Mika, and also from practical issues, this meeting will be recorded. And think it's better that you save your questions to the end, then you will have the questions round in the end of this webinar. So please, Mika.
Okay. So, Frode, can you see this?
Yes.
Okay, then I assume everyone else also sees. So thank you, Frode, and good morning all, and nice to see so many interested people on the line today. So my name is Mika Liukkonen, and I'm working as a research engineer in the R&D department of the Sumitomo SHI FW company, which is located in Varkaus, Finland. Some of you may already know that our company is a global supplier of energy boilers, and during the years we have supplied a full range of CFB boilers totaling 36 gigawatts in power capacity and 30 million hours of operational experience. In addition to the conventional energy boilers, our solutions expand nowadays to long-duration energy storages, flue gas cleaning, gasification, and waste-to-heat boilers. Personally, my main job in the company is the design and development of different kinds of novel digital services for the power industry, which is one of the newer and growing business areas for this company. And one important part of my work is the management of research projects we have with our partners operating in the public and private sectors. And actually all the findings you will be hearing of today are the results from one of these projects. So I will just shortly mention that the research presented in this webinar is a part of an EU-funded project called COGNITWIN that Frode already mentioned here. And the project has 14 partners in total from 7 different countries, of which 6 are industrial partners, 4 technology providers, and 4 R&D partners. The coordinator of the project is SINTEF. The main idea in the project is to cover the whole chain of data handling and refinement from sensors to plant optimization and control, and to create hybrid models or digital twins for the pilot processes of these industrial partners that are taking part in the project. You can learn more about the project by going to the web address written here, or you can also find it more easily by just Googling COGNITWIN. In the power sector, a large variety of technologies is being used to produce the power needed, but in this webinar we will be focusing on circulating fluidized beds, or CFBs. However, it is to be noted that fouling control is very important for all types of energy producing technologies, and the monitoring technologies we present in this webinar could also be used in other types of energy boilers, not only for CFBs. So in this kind of CFB boiler, the process to produce steam goes so that the fuel is first put into the boiler from the fuel silos. You can see on the left colored by green here. The fuel then burns in the combustion chamber here in the mixture of solid matter, and this so-called fluidized bed consists of the fuel and typically sand particles that are being fluidized by the combustion air, which is fed into the furnace through the bottom of the chamber. In the process, part of the material is circulated back to the chamber through a cyclone over here. The cyclone separates the larger particles from the flue gas stream and directs them back to the combustion chamber. So there is this kind of circulation movement. The flue gas and the finer particles continue to the flue gas duct, which is shown as a green area over the furnace in this picture. In the flue gas duct, there are usually different types of heat exchangers located like these red areas in the picture. These heat exchangers are designed to catch the heat from the flue gas flow and finally produce superheated steam that can be used to produce heat or electricity or both. The key benefit of this kind of dynamical process is that it can provide a high flexibility with fuels. This is because the mixing is more efficient because there is a high level of contact between gases and solids. This makes the whole combustion process more stable and also makes it possible to use a wide range of solid fuels and cheaper fuels. So overall, CFBs are quite well suited to deal with current and future market requirements as the fuels are becoming ever more demanding in terms of combustion. However, there are also many challenges in using biomass or waste-derived fuels. First of all, the material is typically very inhomogeneous. For example, the crushed demolition wood you can see on this picture over here. It can contain many types of materials from pallets and planks to old railway sleepers even. So there may also be a lot of foreign matter and variation in the moisture content of the fuel. And also the elemental composition in these fuels may vary a lot. The fuel may be also stored outside under the open air, so that may increase the moisture content of the fuel significantly. What is fouling then? Fouling is one of the problems connected with multi-fuel combustion and challenging solid fuels. By fouling, we mean actually the phenomenon in which some material carried by the flue gas accumulates on the surface of the convective heat exchangers. Due to this accumulation, the efficiency of heat transfer is reduced and the soot removal is needed on a regular basis. On the other hand, excess cleaning is a waste of resources and also exposes the tubes to wear and corrosion. In these left side pictures over here, you can see some typical fouling in this upper picture and some very severe fouling in the picture below. This is a very extreme case, but it kind of shows you what can happen if the fouling cannot be controlled properly. However, the monitoring of fouling is not so easy actually because there are not any feasible methods to do it directly because of the harsh conditions in the flue gas duct. There is often smoke and dust and particles that are in continuous movement. Also, the temperature can be as high as 800 degrees even in Celsius. But still, some estimation on the fouling rate of heat exchangers can be made by modeling and calculation, but typically the fouling rate is affected by several factors like boiler load level and combustion conditions, as well as, of course, the fuel type and fuel quality. And fuel quality is quite often unknown in detail. So this kind of calculation has to be flexible enough and able to adapt to changing conditions. So what are the most typical soot removal methods in boilers? Perhaps the most typical one is steam soot blowing, in which the fouling deposits are blown off with superheated steam at boiler pressure. Those steam nozzles can be moving or stationary, and the steam is typically taken from the primary superheater. Then there is acoustic soot blowing, which basically means directing a pressure shock on the deposit. Typically it is a sound wave, which is made by pneumatical system. This is typically used for heat exchange surfaces in the lower temperature areas of the boiler. Using water cannons for soot removal means washing the deposits off by directing a water jet to the area that is to be cleaned. Those are typically used for evaporator surfaces, not superheaters. Then there is hammering, which induces vibration to the system by some kind of mechanical strike. And this is typically used for very extreme fouling conditions like waste-to-heat boilers and boilers that are using oil shale as fuel. Detonation cleaning is typically one-time operation for these difficult situations in which these other fouling removal systems do not work. So except for this detonation cleaning, these soot removal techniques are typically used regularly by a fixed time interval that has been determined in the commissioning stage of the plant. This time interval between the soot removal sequences can be, for example, once or twice per day when we talk about the steam soot blowing. And it can be much less for acoustic and hammering methods. The main thing, however, is that this kind of control strategy does not take the prevailing heat transfer capability into account. So soot blowing is done regardless the condition of the heat transfer. Our pilot plant, which we have been studying in the COGNITWIN project, is Energia Unit 7 in Västerås, Sweden. The plant has been taken into use in November 2019. The boiler is designed for wood-based fuels, and the typical fuel being used by the plant is demolition wood. Fouling management has been considered important for this plant from the aspect of minimizing the OPEX costs. In this research, we have concentrated on the heat exchange surfaces that are being regularly soot blowed by steam soot blowing. You can see over here. And especially we have concentrated on the first superheat in the flue gas part, which is marked here by the red circle. The use case we have defined in COGNITWIN is twofold. On the asset manager level, it would be useful to be able to ensure that the heat exchange surfaces are being cleaned in an optimal way, for example, from the fuel cost aspect. When we use these steam soot blowers, the steam for soot blowing has to be generated in the process using some extra fuel. So from this point of view, the soot blowing process is an economical loss. However, we also lose some heat due to the fouling of the heat exchanger, as its heat transfer capability is reduced by the fouling. Then on the operator level, it would be useful to just have a clear indication when to start the process of soot blowing and how to do it. Okay, this has been my short introduction to the subject, but before I let Istvan speak about the next topic, I will take the occasion and just shortly let you know that our company has an interesting set of new digital services available, and the services are based on real-time analytics, and depending on the type of the service, they can help in increasing the boiler production and performance, or lowering the operational costs and improving boiler availability and so on. So if you wish to know more about this, you can navigate to this website and learn more. Okay, so this was my introduction to today's topic, and now I will let Istvan Selek speak about the modeling-based approaches for fouling monitoring. Please go ahead, Istvan.
Thank you, Mika. First and foremost, I will share my screen and start my slideshow. And I would like you to give feedback. Can you see the slide shared on your screen?
Yes, we can.
Okay. So thank you, Mika, for the introductory material. And I'm Istvan Selek, representing the University of Oulu. And I'm delighted to be here to share the latest advances we have been achieving with respect to the COGNITWIN project. So the results that I'm going to be sharing, it's a cooperation between the University of Oulu and the Sumitomo company. And I will go a little bit against Frode, who said that I'm going to be talking about the modeling, and a little bit of a correction to be added here. Due to the fact that the time frame is very, very limited, I decided not to talk about the modeling itself, but to talk about how to utilize models in fouling monitoring. That said, I would like to, let's say, introduce a bit of a repetition and just set the foundations for the problem itself. And the problem itself, as Mika pointed out, stems or appears in the operation of combustion-thermal power plants, which you can see in this figure, at least the core devices of an combustion-thermal power plant. So the combustion takes place in this brownish vessel in the middle, and as a byproduct, the combustion produces a flue gas, which, as a matter of fact, has very high energy content in terms of heat, and that is being utilized for the superheater section. That means we are going to use saturated steam and increase its temperature, and this is going to be taking place in this, I would say it's pinkish area of the plant. So the flue gases leave the furnace through this green duct, and then they are diverted towards this pinkish box where the heat exchangers are located, and the purpose of those heat exchangers again is to increase the internal energy, increase the temperature of the steam, to superheat the steam. And what's the problem with this is the fact that the flue gas contains actually leftover materials from the combustion. And Mika pointed out the temperature in this area, in the superheater section, is very high. It can be up to 800 degrees. So the material, the leftover material, which is included in the combustion flue gas, they are going to be very sticky usually, and they are going to form a deposit on the coils of the heat exchanger. And this is usually a typical figure. In this case, the fouling phenomena, so the deposit formation is very severe. And the problem is with this phenomena is not because it looks disgusting. It is actually disgusting, not just looks disgusting, but it is disgusting. But the problem is that with the formation of the deposit on the heat exchanger coils, what we lose is heat exchange efficiency between the flue gas and the steam. And the thicker, the larger the deposit, the more severe of this degradation is going to be. So that means if we want to maintain specified condition with respect to the steam, then we have to introduce more and more fuel to the process, given that this deposit layer is going to introduce a thermal insulation layer on the coils of the heat exchanger. So in a sense, it is a very harmful phenomena, and it is harmful from many different perspectives. And the other, let's say, main branch here, which I would like to mention, but I'm not going to be attending in this presentation, is the corrosion. So that corrosion actually will introduce some damage to the materials. So that is also a very harmful phenomenon. And in this presentation, we are going to be addressing the monitoring of this deposit layer, of this deposit formation via process measurements, so via data. So that's that was our role in this COGNITWIN project. And in the next presentation, Anders Hansen will talk about how do we actually introduce direct measurements to the loop. What kind of possibilities we have for the direct monitoring of the deposit formation. So in my presentation, let us call this approach what we use is indirect monitoring. I mentioned that we have developed approaches which are relying on so-called regular process measurements which are available at the plant. And what are those measurements? If you have a look at the figure, what I'm presenting on the slide, then I will clarify it in a second. So what is the role of the heat exchanger or the arrangement of a heat exchanger can be visible in this figure, where we have a flue gas duct. Flue gas flows through the duct, and that has the thermal energy that has high temperature, and then we want to utilize this high temperature to heat up the steam. So the steam line in this schematic figure is represented by the blue arrow. And with respect to this, in that sense, very simple device or setup, what we usually have available at the plant are typical process measurements, including P, which stands for the pressure, T, which stands for the temperature, and the third measurement type is highlighted by F, which stands for the flow measurements. So these are typically we have available at the plant, and we don't need to install extra sensors, so to speak, to have an estimate on the falling. So our role in this project was to use available measurements, which are these three simple types, temperature, pressure, and flow measurements, to create a tool which is able to give a reliable estimate on the deposit formation, and in particular the efficiency between the flow gas and the steam line. And what the scientists do at the first glance is, of course, build a model based on physical laws relationships. So it's a so-called white box model or first principle model. And this is what we have done. I'm not going to go into the details. I would call it, let's say this is a textbook exercise. So anybody who had classes with respect to fluid dynamics and thermodynamics, in my opinion, is able to lay down the foundations of a simple model which targets the modeling of a heat exchanger. Of course, complexities range from very simple model to very extensive and very complex ones. I would say that our model at the very beginning was just about the energy conservation, introducing some dynamics. So we did not really utilize for the modeling purpose, so for the white box modeling purpose, the literature, which is really heavily tied to the heat exchangers. So just foundational, let's say, basic principles with respect to thermodynamics and fluid dynamics. And then at the end of the physical modeling line, we have actually even noticed that we don't even need a dynamic model to capture the falling phenomena using process data, due to the fact that the falling has a different time scale than the dynamics involved in the fluid mechanical and thermodynamical model. So what at the end we have, it's called a static model, is just a function which represents fundamental energy balances. And then we said, okay, this is our first trial. Using this, let us see that how far we can go with the prediction of the heat exchange efficiency. And this is what you see in this figure. I would like to make a magnification to explain what is happening here. So there are two curves on this figure. The first one, which is marked by blue, and another one is which is marked by red. The blue one represents the efficiency which can be derived from data. This is the efficiency of the heat exchange between the flue gas and the steam, which can be utilized, which is derived via a physical model using process measurements. And the red one is the load level of the power plant, what you can see there. So you can see in the blue curve, which is the efficiency curve, it's kind of a sawtooth looking figure. So that means we jump up in some cases. So that means we increase the efficiency by chute blowing. So this jump up is represented by the cleaning operation. So in that case, the chute blowing operation. So we clean the surface of the heat exchanger. We have high efficiency, and then via time, which is usually a 12-hour period, we degrade. So we lose the efficiency. And if we reach a certain minimal limit with the efficiency, then we inject again and clean, and so on and so on. The problem with this approach is that when the load level changes, so let me just highlight, for example, this case where we go from 100% load to 40% load, this heavily distorts the figure. So on constant load, you can see that this would be even acceptable without any problem. But with respect to the load change, this is definitely a challenge. And in the next stage, we wanted to solve it. And we have tried first and foremost the further development of the physical model, but that turned out a bit tedious in a sense that if we increase the complexity of the model, that increases the number of tunable parameters, and that number of tunable parameters has a certain effect on the outcome. So there is lots of issues with the tuning, and then finally we made a conclusion. Then we just keep our fundamental energy balance model, which is, as a matter of fact, static model, and then we introduce the so-called hybrid part, a data-driven model part, which will actually first and foremost learn so the purpose of this data-driven part is to learn the correspondence between data and the folding factor given by this static block, so given by the fundamental energy balances. And besides the learning of this behavior, it should be able to separate what is the share or what is the change due to the load level and what is the change due to the chute blowing. So this data-driven model is what we utilize. This is known under the name of subspace identification, which is an approach which was developed during the 80s and the 90s. So about this book, this is what I would like to highlight. There are lots of technical details, and again, due to the time constraints, I'm unable to share with you. But again, so feel free at the end of the section when the questions came to put forward your questions. So this is the model what we actually created. Again, the main point here, or the takeaway message, is we have a white box part and also we have a data-driven part, which is meant to learn things and filter out some unwanted behaviors. And this is what I'm going to show you now. So how this is actually working out in the practice. And I will let the tool run a bit, so run some time horizon, and I will explain what is actually happening here. So I think now it's a good time to zoom in and explain briefly about the meaning of this chart. So first and foremost, the figure which is on the top. So this includes the prediction of the heat exchange efficiency due to the fundamental energy balance, which is highlighted by the red dots. And then the data-driven block supposed to be learning the behavior of the prediction. So this output of the blue box is highlighted by this blue signal. And if they are kind of on top of each other, so that means we have done a good job. And after what happens, we want to exclude the effect of the power change, which is highlighted by this figure down on the bottom. So that's the effect of the power change on the heat exchange coefficient or deposit formation factor. And on the middle, that's the efficiency of the heat exchange, or it is related to the deposit formation. So what we are going to see here, when the power change happens as time goes forward, then this figure in the middle should be unaffected. If the dynamic block, the so-called data-driven block, does its job as it's supposed to be. So I hope that the power change will happen soon. So here now the power change is happening, which distorts the original prediction, as you see. So it starts to dump down, but the data-driven block actually filters it out. So it dissects kind of the signal and separates the effect of the power change, of the power change on the heat efficiency, and also the remaining part, which is a much clearer signal. At the final slide, which is my concluding slide, I would like to share you the benefits and the features we implemented during this research study. So what we have built a model which is using only process data to make an estimate on the falling of the heat exchangers in the flue gas duct. And this includes a first principle part and also a data-driven part. So with that data-driven part, we have introduced learning and adaptation, and also we have introduced robustness. So that means it can be easily so this model structure can easily adapt to the unmodeled parts, and easily can pick up, relatively easily can bridge the gap between the model world, so the paper world, and also the reality. And with this comes the benefits. We achieve flexibility, so we have minimal tuning parameters in this case. Portability, where that means we do not have to rely on any special software to be able to implement this. And also on the visualization side, we are able to provide, I would say that a very reliable figure on the falling factor or the efficiency of the heat exchange to an operator. This slide concludes my presentation. I will give the word to Anders Hansen, who will talk about the direct measurement of the falling.
All right, thank you very much. Give me one moment to share my monitor now. Let's see there, I believe I am online. All right, yes, my name is Anders Hansen. I'm with the SINTEF Research Institute and the group known as Smart Sensors and Microsystems. So we, among other things, develop sensor-based solutions for process industry with emphasis on developing robust inline solutions that work in demanding environments. The process industry is, of course, full of demanding environments. You have high temperature processes, you have abrasive environments, toxic environments, you have mechanically hazardous environments, dust is a particularly pernicious environment. It has a way of combining with the others. You get hot dust, abrasive dust, corrosive dust, you get the idea. There are lots and lots of different ways in which you can have a demanding environment that makes it difficult to install, deploy, and most importantly, trust a sensor. As for the Sumitomo use case, the challenge, as we have learned, was to monitor the fouling buildup on the heat recovery surfaces inside the flue gas duct. The flue gas duct is an incredibly hazardous, harsh environment. It is high temperature, it's dusty, corrosive, toxic. It in fact checks every single one of the boxes above, and that makes it very challenging to deploy sensors. You certainly cannot install anything on the inside of the duct. The best you can really do is to install something on the outside. Before I go on, I really should mention that the motivation for the work that I'm presenting here came at the outset of the COGNITWIN project. Now, Istvan showed you the results of these thermodynamics-based calculations, the energy balance calculations for monitoring fouling. However, these calculations use a huge number of data inputs. And the more data sources you have in a calculation, the more you're making yourself vulnerable to data quality issues. You have single point failures. You have the risk of a sensor misbehaving without you noticing it in your model. And generally speaking, error propagation becomes a more and more punitive landscape the more data sources you bring in. So at the outset of the project, it wasn't clear whether this would deliver a good result. So we decided on a two-pronged approach where there would be a sensor-based solution where we would try and develop a single data source to see how well that could monitor the fouling buildup. Now back to that, we chose an acoustic solution. The basic idea is one that I think most children know from Christmas Eve. If you shake a closed system, then maybe, just maybe, you can learn something about what's on the inside. To be a little more sophisticated, you have a field of science known as modal analysis. This is used, for instance, by mechanical engineers who develop, say, automobiles. And it's a way to investigate whether there are underdamped mechanical resonances that could, for instance, cause your car to start shaking dangerously under certain conditions during driving. Similarly, for, say, an airplane fuselage or other systems, in civil engineering, modal analysis is used to look for dangerous mechanical resonances. For instance, I think most of us know the story about the bridges that collapsed due to soldiers marching over in lockstep with a certain frequency, or the story of the Tacoma Narrows Bridge that collapsed because of certain wind conditions. To the best of our knowledge, this is the first time modal analysis has been used as a tool for condition monitoring something over time as an online sensor. So we're really starting from scratch here. And in addition to the modal analysis scheme, we're also using the raw data in a passive way to listen for background effects. Together, these comprise a hybrid approach where on the one side you have a purely physics-based approach to fouling detection, and on the other hand you have more of a passive blind search using data-driven tools. Sumitomo has some very skilled mechanical engineers. They have, using FEM simulations, given us some predictions about the mechanical or acousto-mechanical properties of their heat exchangers. The plot you see here shows the vibrational structure simulated for a heat exchanger. And the peaks that you see along here are vibrational resonances. So that, for instance, they predict that there'll be a vibrational resonance at approximately 5.4 hertz. And furthermore, they've simulated the effect of applying fouling to the coils, which will tend to shift these resonances downward. The reason they shift downward is that when you apply mass to a mechanical system on a spring, that tends to reduce the resonant frequency by this, textbook formula that I'm sure many of you have seen. The frequency goes as square root of K over M. The other thing that was uncovered in these simulations was the expected magnitude of the response of the coils, which is very, very weak. The top line here is 1 milli-G, that is 1/1000th of Earth's gravity. It's on a logarithmic scale, so you get a factor of 10 lower before you really hit any of the resonances. And this is a huge challenge because although these very, very weak vibrations are not below the noise floor of our sensor, they're definitely below the noise floor of the plant, which is, generally speaking, a vibrationally noisy environment. So very careful filtering is required to actually detect these resonances. To extract these weak signals, we use a technique known as lock-in amplification. This is used in various fields, most notably radio frequency engineering, and it underpins the way the FM radio in your car is able to extract extremely weak energy levels from the airwaves and filter out a single frequency to play music on your car radio. The way we use it is we have a PC that is connected to both the sensor and the actuator. The PC provides both synchronization and data logging, as well as first level analysis of the data. The shaker and sensor are both connected to the steam pipes via these mechanical signal rods, which ensures that we can keep sensitive equipment on the outside of the hot zone in the power plant. And the lock-in amplification scheme means that you're mixing the synchronization signal going out with the sensor signal coming in, and the output is a so-called phasor. A phasor is a complex number, which is to say that it lives in sort of the two-dimensional phasor space and has the nifty feature that when you scan the frequency across the resonance, the phasor will trace a circle in this two-dimensional space. This circle is what is known as a universal resonance function, and it's, again, basic textbook physics that can be applied to the system. The circle has the nice feature that if you decompose it into X and Y components, then along one axis you get this Lorentzian resonance peak, and then you get an error function on the other. This error function, and by the way, I should mention here that each plus here is a measurement, and you can see that in total they fit very well to this heuristic universal resonance curve. The advantage of it is that it is very useful for locking on to the resonance. So you can use a PID feedback scheme to make sure that you're always shaking the heat coils on resonance, and then the set frequency plods along, and you can use that to trace out a time series. That's what we've done here. So you can see here how the inline measurement traces out the resonance frequency of the coils over time, and as predicted, it trends downward when fouling accumulates, and each time there's a soot blowing, which is marked with sort of a vertical line on this background spectrogram here. Each time a soot blowing occurs, it pops back up, so you restore the initial condition, the original condition of the fouling monitor. And at this point, I have to emphasize all of this comes from a single sensor, a single data source, and only physics-based modeling. There's no machine learning involved yet. So this is completely physics-based measurement. In addition, as I said, we wanted to take all the other data after we had filtered out this response to the shaker. We wanted to filter out and ask if we just listen to everything else going on. You know, oh, Zen thing. Can we learn anything? We expect to have lots of ambient sound in a plant like this, from the flue gas, from the steam in the pipes, etc. Is there something we can learn about the process in this way? Our approach has been to convert the raw data into spectrograms. This is a sort of niche field known as acoustic chemometrics, which is a marriage of of quantitative chemistry with mechanical engineering. And what you do is you convert the data into the spectrogram, which is a hybrid representation in the both time and frequency domain of the data. You learn about the amplitude of the background noise as a function of frequency, as a function of time, and you can treat each frequency component as a sort of virtual sensor, if you will, which provides a time series. And then you use your favorite multivariate analysis technique together with whatever training data you have available to try to extract meaningful features. This is an incredibly simple and somewhat naive approach. A few lines of computer code is all it takes. Also, there are real reasons to be concerned about acoustic chemometrics because, for instance, it doesn't take into account the highly nonlinear nature of acoustic waves. And yet, when you just plug it into your favorite program, MATLAB in this case, you get really good results. So on this plot, you can see the orange curve, which is University of Oulu's thermodynamic model, Kalman filtered, whereas the blue dots are raw data. Each dot represents a single column of the spectrogram run through a PLS regression analysis. Minimal effort and rather good results. Again, this is a single sensor giving you all this in addition to the physics-based data that I showed you before. So to conclude, we're very happy with how things have gone with this project. From a single sensor and the data set, we have both physics-based data and a data-driven model. And the next step is to both refine these analyses, but also to merge them in a way that extracts the strengths of each of these different techniques. We're also hoping that we can work on finding more sensitive sensors that can improve our signal to noise ratio and improve the bandwidth of our regulation scheme. And all in all, we're very happy with what has happened and we're happy with the way things are going. And finally, I really need to thank my team who have been working on this and really pulled together lots and lots of fields of expertise to develop this sensor-based solution. And with that, thank you very much for your attention. And I think at this point we can move on to questions for all three of us.
Thank you, Anders, Istvan, and Mika. Then we have this question and answer part. So we agreed that you will take the lead there, Mika, and then I just open up for questions. So please. No. Then
I have a question, Frode. I was thinking this is very neat methods, which I believe in this hybrid thinking. Is Sumitomo looking into this as a product at the end, kind of an add-on into their systems, kind of digital product, and how would you like to implement it? Because with so many technologies together, it's quite complex to put it into a product structure.
Yes, you know, we are continuously kind of looking new solutions and better solutions for this kind of fouling monitoring and optimization. We already have one product which is quite simple, more simple than developed in this project, but it has certain limitations. So we are, of course, looking for better applications. So it's definitely an option after this project to look at the final results and consider those as a next generation product for us. About the acoustic sensing application, as Anders mentioned, it's kind of early stage technology. So in this project, we do not have the resources to kind of finalize the results to this kind of project. So in that area, we are more looking into future research projects to have more experience on that technology.
Oh, thank you. It's very interesting.
Thanks. Is there more questions?
It don't seem so. So then I would like to thank you all again for very, very interesting presentations and for all of you who attend this breakfast webinar. Okay, thank you all of you. Bye then.
Bye.
Thank you.
Bye.
Bye.
Bye.